LiDAR stands for Light Detection and Ranging. It is an aerial mapping tool used by utilising lasers to measure specific distances which, once processed, form shapes. LiDAR can be used on ground level or from the sky. For my dissertation topic, I utilised airborne LiDAR data to reduce faults on the Scottish Power Network. Airborne LiDAR scans from 2,000 feet, scanning the land in 300-metre swaths. This creates a grid over the ground which has 40 points of reference per metre, so 1,600 points per square metre. LiDAR data processing requires the company intender to reduce down the initial petabytes of data gathered by LiDAR down to terabytes, so it can be managed and used to benefit the company utilising it. Other uses of LiDAR out with the energy industry are asset management, mapping, after natural disasters for planning, and even in architecture, where ground-level LiDAR are used to log precise details of historic buildings when restoration work is required. An example of what LiDAR can produce can be seen here. On the left, we see a picture of a tunnel, and on the right, we see the grids that LiDAR has created and the form of the tunnel made by LiDAR scanning. The energy companies currently utilising LiDAR can be seen on screen. The significance of energy companies utilising airborne LiDAR is notable due to the roots of the leading company offering LiDAR technology. ROMES, which stands for Remote Observation Automated Model Economic Solution, is a data mining technology created by Australian energy provider Argon Energy. Argon created ROMES back in 2011 to address the ongoing issues they faced where engineers were putting their lives at risk, travelling, often alone, outback to desolate areas trying to locate faults. Due to regulators deeming their sole access to this technology as giving them an unfair competitive advantage, they were forced to sell ROMES in 2014. They sold ROMES to Fugro, a Dutch multinational company, and thus Fugro ROMES was created. The rich picture below shows at a high level the process by which ROMES is utilised. Planes scan the network per zone. Cartridges with petabytes of data is couriered to Australia, where it's processed. Fugro ROMES provide detailed insights into every located asset and use the LiDAR data as well as the photography to create bespoke virtual world asset management maps for companies to use. So, at a high level, I will now discuss the various capabilities of LiDAR and ROMES. 3D scanning of the network, as well as detailed photography to give accurate topography and create ROMES World, their in-house equivalent to Google Earth. It also has simulation capabilities and can complete jobs currently done manually through the use of various algorithms. 3D scanning can be seen here. The left shows the LiDAR asset location and scan creation. The right shows the scan layered with a photograph of the area as you would view it in ROMES World. Each laser beam measures the distance at which it's cut off to determine shapes and sizes of assets. Photography and topography is another significant aspect of ROMES and LiDAR. Here, the original mapping method can be seen versus the new method on ROMES. Here, the clarity of the topography can be appreciated. If we compare this with the 2D nature of Google Earth, we see the benefits of utilising laser scanning along with photography. Simulation is another tool provided by ROMES. Again, through the use of complex algorithms, ROMES is able to imitate various situations such as natural disasters and extreme weather conditions. This is vital for the energy industry. As you can see on the right, we have an overhead line with all the load on one conductor. This may be due to a fault having occurred. The extra load on the left causes the overhead line to hang lower, therefore being more likely to come into contact with the likes of vegetation. If this were to occur along with a fault, this could cause a black start situation where no energy would be transmitted across that line. ROMES allows situations such as this to be simulated, along with the likes of severe weather, where the impact of, for example, high winds on a circuit, like this, can be measured and allow for potential faults to be mitigated. Finally, for the energy industry, ROMES can complete jobs which are currently completed manually, such as measuring ground clearance or vegetation clearance of lines and conductors. This reduces costs and ensures greater data integrity. There are, of course, some limitations of LiDAR and ROMES technology. It's only as reliable as the day the scan took place, as is any audit. It's unable to perform certain functions efficiently, such as capturing heat signatures. To fly low enough to achieve this would increase the cost by 700% due to the limited area you can scan at that low height. LiDAR requires dry weather to scan efficiently due to lasers reflecting off of water droplets. This is obviously not ideal in Scotland. Due to the data needing to be couriered to and from Australia, this lengthens the process considerably. So, I've mentioned on several occasions the fact that ROMs use various algorithms to measure the data and transform it into useful information. Due to the nature of LiDAR and ROMs technology being at the forefront of their business, they are, understandably, not publicising the exact means by which they are processing their data gathered from LiDAR. In a journal article written by Nupur Bhatnagar of University of Minnesota, the process by which LiDAR data is mined is presented clearly. ROMs utilises spatial data mining. This is the process of finding hidden patterns in large datasets. The term spatial dataset refers to the data that relates to location and spatial dimensions of geographical entities. When we consider the nature of the data present in ROM's world, there's a definite link here. A large spatial database, such as ROM's, contains different spatial types. To extract patterns from this data involves finding correlations that exist in the data. Spatial data mining uses different classification, rule mining and clustering algorithms in order to conduct both supervised and unsupervised learning. The basic purpose of all of these algorithms is to build a descriptive model that will enable categorization of objects in different categories, or a predictive model that will predict the future, based on knowledge from the domain. The model produced by spatial data mining algorithms is such that the model could be used to predict the outcome of future situations. Challenges arise because where traditional data mining deals with discrete and continuous variables, this deals with complex and rich variables, comprising points, lines, and polygons. Spatial data mining comprises implicit attributes, where traditional data mining would contain explicit attributes. Spatial data has strong autocorrelation, where different spatial variables are correlated with each other, whereas traditional data mining focuses on independence of variables. Spatial data mining research has drawn on a number of other fields, especially inductive learning, machine learning, and spatial statistics. Inductive learning is a model of building process where the database is analysed with a view to finding patterns. Similar objects are grouped and classes and rules are formulated. The nature of the database is dynamic and must be adaptive, so it must be able to learn. This is done, again, through supervised and unsupervised learning. Supervised learning being from examples, unsupervised being learning from observations and discoveries. Spatial statistics are the second topic. Statistics have a solid theoretical foundation, although the issue that's faced is that they're often difficult to comprehend without guidance or explanation of where or how to analyse the data. Thirdly, we have machine learning. Machine learning is concerned with the development of algorithms and techniques that allow computers to learn. We have two levels here, inductive and deductive. Within inductive, we've got creating computer programs by extracting rules and patterns out of massive datasets. Deductive, we're working on facts and knowledge and deducting new knowledge from old. Within this, we have pattern recognition. This can be defined as the act of taking in raw data and taking on action based on the categories of that data. It's a collection of methods for supervised learning pattern recognition and aims to classify data based on prior knowledge or on statistical information extracted from patterns. So, by combining all of these elements, ROMS has been developed into a piece of software which leads aerial mapping, LiDAR technology, and makes it a key competitor in a variety of industries for virtual world asset management.